he's supposed to introduce you. But he's late.
Quite sorry.
So I was about to take over. Please.
Thank you. It's my pleasure to present Professor Terry Rockafeller as a plenary speak in the 50th anniversary of IMPA, and optimization group at IMPA, and also IMPA is pleased to present him because he has outstanding results in the field of convex analysis, optimization, and also set value analysis and variational inequalities, which is the field which he is researching now, and he will talk about the role of set value analysis in optimization.
Thank you. It's, of course, a great pleasure to be here to participate in congratulating IMPA on its 50th birthday and all the successful research which has been undertaken here. It's also a pleasure to represent an area in which a lot of good contributions have come from IMPA, and that's the area of optimization and the numerical methods connected with optimization. To many people, optimization may not be a familiar subject because it's not part of the classical tradition in mathematics, at least directly. It is, to some extent, of course, an important area of applied mathematics with a wide range of applications. However, I think for many of you, the most interesting thing about it may be the interactions between this area and other parts of mathematics, specifically analysis and variational problems, variational analysis, and things like that. So in this talk, which is aimed at a general audience, I will not say very much about the details of the new contributions, in particular coming from IMPA or myself even, but try to give you a picture of this subject and how it fits in with the concentration on this theme of set-valued mappings. Now, when I was a student and got my mathematical education, set-valued mappings were not popular. In fact, they were completely out of fashion. One was not supposed to mention. There was no such thing as a set-valued mapping. Set-valued mappings were considered to be things like multi-value. There was a contradiction in terms to have such a thing. But gradually, at least in the subject in which I work, it has become more and more apparent that these are important objects that need to be studied from a slightly different point of view. So, of course, what is a set-valued mapping? So, in some way or another, it's a way of associating with a given point in some space a set that's in another space. Now, one way to think about it, of course, is that it's a single-valued mapping into a space of sets. But that is the framework which has turned out to be very inconvenient, one could even say wrong, for the applications that have to be made. So perhaps I can show you why these mappings are important. So by the way, in my own work, I try to distinguish between, you may not like this, but I try to distinguish between a function and a mapping. I would never have a set-valued function. And when I have a mapping, of course, it could be single-valued or set-valued. This, by the way, is one of the main issues. When you treat set-valued mappings, you want to allow them to be single-valued as a special case, and that doesn't fit with the framework of a mapping into a space of sets. So one of the things I wish to explain is why the study of optimization has led to development of mathematics, not only some new mathematics. Everybody's research leads to new mathematics. I mean, we hope. But to something more like a new paradigm. So I'd like to explain why certain very fundamental shifts in points of view, not only about set-valued mappings, but other aspects of how to think about mathematics, become important. So first, I need to explain to you something about optimization. There was such a thing as optimization for a long, long time, but it was not called optimization. The word optimization comes from the period around 1950 and the advent of computers. What was optimization in the old days? Well, of course, there were the things we know about, so-called Fermat's principle, how to find the top and bottom of a curve by looking at where the slope is zero. Things like this from the calculus. Those things were around for a long time. But as a very substantial mathematical subject, optimization started with the calculus of variations and the Bernoulli brothers. And of course that went into the calculus and Newton, and to many people even the word variational problem refers necessarily to an infinite dimensional problem in the calculus of variations. But much of this changed around the 1950s. So first of all, of course, anytime you have a problem of optimization, that in some sense refers to minimizing of some function over some set. A real valued function, because you need an ordering to do a minimization, and real numbers are the best. So you could also speak about maximization, but all you have to do is multiply the function by -1. So we don't need to focus on maximization in the theory. Now there's such a wide range of problems, and incredibly important problems in which a lot of money is going and a lot of research is going and computation. But aside from the problems in the calculus of variations, where the basic element, unknown element, is a function, a typical thing would be continuous optimization, where you have a number of real variables, let's say. But many applications also involve discrete variables, combinatorial optimization, or even Boolean or logical variables. Should you do it, should you not do it, and so forth. And but I can't talk about everything. For this purpose of the talk, I'll talk about the area that's both simplest and closest and most easily available for explaining ideas, which would be what's called continuous optimization in finitely many real variables. So there, the unknown element about which some decision is going to be made can be viewed as a point of Rn. So we have n variables, we put them together as a coordinates of the vector, a typical trick. And then the set over which we want to minimize is some subset of Rn, or of course it could be Rn itself. Then you have to realize that in such a problem there's more than one idea of a solution. Because one idea would be the minimum value of the function, the number as a solution. But another would be what point gives the minimum. That's what we call an optimal solution. But here we start to get into something special, because there is in general no reason to suppose that this point would be unique. Now, in optimization, there's still a third concept of solution, a preliminary concept. All the points of the set over which this minimization will take place are called feasible solutions. It just means they satisfy the constraints of the problem. Now, one of the things that one does in optimization theory is try to characterize optimality. This is, of course, the area that students are most familiar with in the beginnings of the calculus. Things about first and second derivatives. You get necessary conditions and sufficient conditions. But there's a big difference already in the way people think about these things nowadays. So necessary conditions, of course, may not be sufficient. If something satisfies necessary conditions, we often call it a quasi-optimal solution. And in many situations, all we can hope to do is find quasi-optimal solutions and then try to go on from there. However, in classical theory, it's all focused around having necessary conditions and sufficient conditions being very close to each other, and then hopefully narrowing it down so you have a few candidates, and then you could decide what was optimal. All of that is out the window now. I'll try to explain why. It's not that it's invalid mathematically, but nobody would ever dream of solving a problem in that way. Optimality conditions now are more frameworks on which to hang a computational method, because the size of the problems, the complications go way beyond anything that you could solve by identifying some candidates and checking them out. Another thing is this question of wanting a global minimum or global optimum, and typically there is no way to get a global optimum, not to mention a unique one, without some idea of convexity. So this has elevated the concept of convexity to be of very great importance in this whole subject. I'll explain some things about that. So where are set-valued mappings? You can already see some hint of them in what I'm discussing here. So we have several concepts of solutions, feasible solutions, optimal solutions, quasi-optimal solutions, and in each case, they could be a set. The feasible solutions are inevitably a set, but the others could be a set of things. And now, any problem depends on some parameters. So if you want to look at these solution sets as how they depend on parameters, you must talk about a set-valued mapping. And of course, there are many ideas that come up. What are the continuity concepts that are appropriate, or semi-continuity? Can you, in some sense, differentiate a set-valued mapping, semi-differentiate, whatever it is? So these are ideas that have inspired quite a lot of people, and in which quite interesting results have come out, although there's no time really to discuss them now. Anyway, you need to look at those I will say something about them. That you need to look at these set-valued mappings not only for optimality studies, for characterizing things, but for the numerical schemes that you build and for studies of perturbations, about how the sensitivity or stability of solutions to parameters in a problem. Now I'll do my best to try to explain this paradigm shift, why things became very different in optimization. So I'm focusing on this continuous optimization in Rn. So what is the classical framework for optimization? You can think of this as what comes out of the calculus as it would be understood by students of advanced calculus. What could you do about optimization? First of all, if you had any constraints at all, there would be equations. And we all know that as mathematicians, we are to some extent identified as equation solvers. It's thought to be almost synonymous with mathematics. That's one thing that you will see shift away here. Another thing is, because of the whole technique of calculus depends on taking derivatives, therefore we have a tendency, at least if we work in this classical framework, to assume everything has derivatives and then exploit the techniques of the calculus for those derivatives. However, in optimization, it was quickly learned that these tools were not adequate. You really had to do some different thinking. Another thing about this classical framework, which fits the idea of maybe identifying some candidates for solutions and eliminating them, is this low dimensionality. I remember when I was a student, and say back in the 50s and 60s, and I would look at older papers, say from the 30s, a lot of the things in those days were written in 2 or 3 dimensions. Somebody wanted to explain something. They thought it was enough to explain it in 2 or 3 dimensions, and then, somebody wants to extend it to higher dimensions. All right, well, maybe it could be done. It just wasn't in the concept of working in higher dimensional spaces. And we'll see in a moment that optimization is characterized by very high dimensions, if not infinite dimensions. Now, in making this distinction now, I'd like to start by, maybe just go on with this and I'll come back to this. I would like to explain a concept of a difference between prescriptive and descriptive mathematics. Maybe I'll start with that for a moment here. So a lot of this classical mathematics came from physics. And physics is a theory of laws describing nature, how things are related, how they act, how they move, and it's governed by equations in almost all cases. At least the way people thought about it, it's always governed by equations. So you could say this is the mathematics that comes of describing how the world operates. But what happened in around 1950 when computers came is that it became possible to consider much larger, much more complicated problems in prescriptive mathematics, where people are trying to make choices. Now, there are any number of ways this could happen. Part of it could be related to physics and engineering, for example, the design of structures or mechanical things. But there's also problems of economics and management of systems, inventories, Enormous range. Electrical power, how to generate, what to do, when. Such a huge array of applications. And these problems are so complicated that previously people could not think about them. There's no mathematics for them. It's not that they are just bigger problems. They have a character which is different. And here is the essence of the character, why it's so different. In all of these cases where you have a range of choice, the choices are limited. But they're not limited by equations. They're limited by bounds, upper bounds, lower bounds. And that means that the variables must go within certain ranges. But they can hit the top. They can hit the bottom. It's okay. So you have one-sided constraints, inequalities, which are crucial. So one way to see it is that variables must go within a range, say a closed interval. But the same then goes for the values of functions. They are some variables, and they are in some range. So, and certain things have to be non-negative. You produce some goods. The amount you produce has to be non-negative. You could produce 0 or positive, but you can't produce negative. So you get into inequality constraints as being absolutely fundamental. Now, in this framework, you cannot just assume that the function you wish to minimize is smooth. By smooth, for me, this is just a word that refers to C1 or C2 or something like that, not C infinity. And I'll explain here why. But the set over which you minimize is closed, and you must be concerned with the boundary. The set may be given in part by equations because they may just represent some relationships between certain variables. It's convenient to introduce several variables that are related, and instead of solving some relations for some variables in terms of another. But the critical part here is that there are inequality constraints, and you do want to hit the ends of them. You might be at the top or the bottom of various ranges, and that means that you must be concerned with the boundary of the set. So in this picture, I try to give a little indication. If a single equation would define a hypersurface of some sort, then on a heuristic level, a single inequality would define something like a curvilinear half space. And when you impose a number of these, you're intersecting such curvilinear half spaces. So it's hard to represent all the pathologies that could arise, so let's not speak of pathologies, but you can imagine a set which is intersection of a bunch of curvilinear half spaces. And now if you wish to minimize a function over this set, you must be prepared that the minimum will occur on a boundary. It could occur somewhere in the interior of the set, but if that were true, what was the point of all those constraints? In fact, the constraints are important. So quite likely the minimum will occur on the boundary. And then you have all these issues. Some of these constraints, you can distinguish between constraints that are essential or redundant. This has to do with their effect on this set C. So in my picture here, for example, this is a redundant constraint. If I remove it, it won't change the set C. Now there's also, though, the idea of active and inactive constraints. They depend on where the optimal point or points might be. So for example, if this is the point that turns out to give the minimum, at that point these things are active constraints, and these don't matter anymore. I could remove them, and I would still have a minimum here, perhaps. But the problem is, trouble is you don't know in advance which constraints are essential or redundant, or which are active or inactive. So there's something inevitably combinatorial about this kind of thing. And anything like optimality conditions must cope with all of these complications. Now, sometimes I am told about complications in mathematics, and I say, well, they're great, those are great complications, so I won't bother with that subject because it has difficult complications. But here, many things have been done successfully with these complications. Now, just a word about the non-smoothness of a function. The functions we want to work with in optimization are often defined by operations of optimization themselves. The function value is already the output of some other optimization in one way or another, maximization or minimization. And here I've given an example where the value of this function is a supremum. I wrote it here as if it's a discrete index, but there could be something continuous there. So this particular idea you could understand as something about a worst case. I want to minimize something. Think of it as a cost. The trouble is I don't know exactly which cost function applies, because maybe there's something in the future, and I don't know which one will be presented to me later. So I could look at the worst of all possible cases. So graphically, that means taking the upper envelope of this collection of functions, and it's obvious that even if these functions fi are smooth, the function f can fail to be smooth, at least at a number of points. Well, it's smooth maybe almost everywhere. It doesn't help, because typically the minimum will occur at a point where it's not smooth. So you cannot fall behind some idea of it being almost everywhere. That is not going to be satisfactory. So to deal with all of these things, a lot of forms of analysis have been developed. The very earliest examples in the early days of computers help to explain some of this. The term linear programming you've probably heard. In the early days of computers, programming was actually a synonym for optimization. Programs were government programs, and government programs, computers were being used to make decisions in government programs. And those those decisions had to be optimal, right? Governments always do everything optimally. So in this case, they did linear programming. So linear programming was a particular model in which you minimize, you had finitely many variables, you minimize a linear function, f of x here, I've written it here as a dot product. You're minimizing a linear function of these variables x1 to xn, subject to a system of constraints, which I wrote out here as a system of linear inequalities and also non-negativity conditions. This is one of the canonical ways that linear programming problems can be expressed. So if that's the problem, what is the character of this problem? The geometry of it you can see here. Each of the linear inequalities defines a closed half space. Then when you're looking at the points that are feasible, that is, the points x that satisfy all of these conditions, they will be in the intersection of all these half spaces. So the set you are working with is what's called a polyhedral convex set, something that can be represented as the intersection of finitely many closed half spaces. This is not the kind of set around which classical mathematics has revolved, except, of course, for the classical polyhedra that Kepler was so interested in, all that sort of thing. So this is a set in which already something different is happening. Now, you can already see also some of the differences in analysis that are going to take place. So if you're minimizing a linear function, it has a constant gradient. I've written it here as c. And then the level surfaces, constant values for this function you're minimizing, they form a family of hyperplanes. And when you wish to minimize, you're trying to find the hyperplane that's the lowest among all of those that still touches the set. And in my picture, it turns out to touch the set at a unique point. There is a unique optimal point, and it's a corner of this thing. Now, suppose I begin to consider how the solutions of this problem depend on parameters. Let's just consider how the optimal solution depends on parameters, and let's only consider, for now, the parameters in the function we're minimizing, the c. So suppose I take this vector c and I change it slightly. I drew this picture in such a way that you can see the following. As I change, let's just think of tilting the vector over again. For a long time, as I tilt the vector, well, for some time anyway, the optimal solution will stay constant. But at a certain moment, all of this segment will become optimal. I will jump from having a single solution to a segment of solutions. And then if I continue to go farther, the solution will be over here, and so forth. So here you see a mapping which is set valued. The mapping from C to the optimal solution. Set valued? Well, it's single valued at most places, but it's not a single valued mapping. It's definitely set valued because of these things that can happen. Of course, this is just a small picture in 2 dimensions. More complicated things can happen in higher dimensions. And of course, other things that could happen with parameters are as you shift these other things, maybe these constraints are tilting or moving in and out. So they could have various effects on this. And you can see something like the following. Suppose all this stays the same, but this thing moves. And for a long time, nothing will happen. But at a certain time, it will hit this, and then it will start to move away at a certain rate. So you will see a kind of effect in derivatives. The rate of change, nothing would happen, and then suddenly there will be a jump in the way things happen. So there inherently are discontinuities in the behavior of these things. Now, a simple extension to this would go to piecewise linear programming, where we have the same kind of set, but the function we wish to minimize is a maximum of finitely many linear functions, affine functions. And notice, by the way, that the epigraph, the set of points on there above the graph of the function, is a polyhedral convex set. This is also a signal of a shift in analysis, because in much of optimization, and certainly and this began with convexity, the focus started to go away from studying the graph of the function, which here is not a very simple or nice object, to studying instead the epigraph of the function. Epigraph is a much more convenient object of analysis for a function than the graph for purposes of a lot of optimization theory. So let's get into convexity now. What you are seeing in this picture is a key idea, because it's so related to things like the fundamentals of calculus. I'm sure at some stage you have explained what derivatives mean geometrically. So this involves looking at a curve and doing things like taking tangent lines or planes or hyperplanes to a curve or surface, and the other hand, a normal line or something like that. And this is the geometry, the fact that graphs of functions in calculus are themselves some sort of smooth manifold, and such a manifold has a tangent space and a normal space. This is the way the analysis has proceeded. But here you see a different type of thing happening, because we are obliged to work with convex sets. There's no way to think about this as a smooth manifold. The surface may be smooth or may not be smooth. In linear programming, it is not smooth. We don't want to limit ourselves to just that. And yet, there are generalized notions of tangent and normal, which are very effective. So in my picture, I've drawn the two objects that are associated with this set at a particular point x bar. One is the so-called tangent cone. It's a closed convex cone corresponding to all these green things. And on the other hand, there's the normal cone, constituted by all these blue things. There's a direct definition. You'll see it in a second. But this is the picture. And these cones have a relationship that generalizes the relationship of orthogonality between a tangent space and a linear and a normal space in the classical analysis. This is the relationship of polarity in convex analysis. Each of these cones can be derived from the other by the process of polarity, which includes orthogonality. Now, here is the direct definition you can give of the normal cone. The normal cone at x bar consists of all the vectors v satisfying a certain inequality for every x in C. This, by the way, is the source of the notion of a variational inequality, which is going to come up in a moment. It's this condition describing the normal vectors to a convex set. And one of the important things about this, although to make the picture interesting, I put x bar to be a kind of a corner point of this set, x bar could be in the interior of the set. And if it's in the interior of the set, this reduces to just the zero vector. So you have in this concept some way of treating the variational of the geometry of a complicated set, even though you don't know where you might be on the boundary. Now, I didn't mention what it says here up at the top. is something I like to say, because it's true. We like to say things that are true, obviously, but so often you hear that in mathematics, the big distinction, especially in applied mathematics, is between linear things and nonlinear things. But in optimization, it's between convex things and non-convex things. For convex things, you have all sorts of special things, and you can use those to approximate non-convex things. So in this picture, you see some set-valued mappings. One is the mapping that associates with each point of this set the tangent cone at this set, and another is the corresponding normal cone mapping. Now, by the way, there are generalizations of this to non-convex sets. They started with my former student Francis Clark, but many people have worked on these now, and this is a very highly developed subject, but it's not the topic today. I'll only be talking about these ideas in the convex setting. Here's how these ideas are connected with optimality. So, to explain this, I'm going to consider the case of minimizing a smooth function that is not necessarily convex over a set, which is a closed convex set, and I'm going to describe the general optimality condition that one can state. First order type condition, a normality condition. So the necessary condition, there's a picture of it in a moment. The necessary condition, I guess we can get the picture there right away, is that the negative of the gradient should belong to the normal cone. And you can see this very easily. In this picture, the green lines represent the level surfaces or iso lines for this function. The gradient points in the direction of increase. The negative gradient points in the direction of decrease. And at a point giving the minimum, then the negative direction here has to be in the normal cone to the set, that point. And in the case where the function being minimized happens to be convex, this necessary condition for a local minimum becomes a sufficient condition for a global minimum. And notice that this condition has the virtue that if the minimum point is in the interior of the set, at an interior point, the normal cone reduces to just the zero vector, so then the condition just becomes the classical principle of Fermat, the gradient equals zero. It's just the first order necessary condition at that point. So all of that is covered by a single relationship. And uniqueness, by the way, is something you could get out of strict convexity. Now this concept is the start of a whole industry of important mathematics connected with variational inequalities. Although the term variational inequality started with infinite dimensional applications involving partial differential equations, the whole thing also applies in finite dimensional continuous optimization and elsewhere. So this is a versatile generalization of the condition I just gave you. So we have a closed set, but now instead of a function, f, a real valued function, we have a mapping from Rn to Rn, which is, in this case, a continuous single-valued mapping. And we have a condition relating f to c. And this condition is the one there. The negative of the value, f of x bar, should belong to the normal cone to the set C. And according to the definition of the normal cone, this is the same as the system of inequalities that you see written here in blue, this system. And it's somehow out of that way of writing the condition that the term variational inequality arises. But personally, I greatly prefer using the normal cone, and I'll try to show you why this is true. So this is the same picture as we saw for a function, but now we're just dealing with a general mapping, not necessarily a gradient mapping. So the special cases of it that are easy to recognize are, one would be the one where f is a gradient. That's the optimality condition we've been looking at. And there are other applications in optimization, however, where this mapping comes out of a Lagrangian function for a problem with constraints. I won't explain the details of that. Other substantial applications of variational inequalities occur in economics, representations of equilibrium. Economic equilibrium can be represented as a solution to a variational inequality in a lot of cases. And then, as I say, there are the applications to PDE, which are, well, essentially partial differential inequalities. But this is just a condition. This is just a definition. What can we do with it? How can we analyze it? And at this point, the critical thing turns out to be to try to understand this set-valued mapping NC, the normal cone mapping as a set-valued mapping. What are its properties? What is its graph? What can you do with it? Now, that's also part of a somewhat larger subject with the same character, subgradient mappings. Once more, there are extensions beyond convexity, but I'm only explaining here the convex case. Now we look at a function, a convex function, but out of our experience we have found it's necessary to treat functions that can take on infinite values. This is partly because these functions may arise from optimization, and in a process of optimization, the optimal value might be infinite, depending on various things. Or you can use plus infinity to represent constraints through an infinite penalty. So now we imagine a function with values in the extended reals. Right? Now, how could you study such a function? By its graph? That's not convenient, because the graph of this function would be in the product of Rn with R bar, the extended reals. And that is not a vector space. The graph of this function is not a convenient thing on which to hang analysis. But the epigraph is. The epigraph is, it belongs in this case to Rn cross R, and therefore can be analyzed by various means. So anyway, a function is convex if and only if its epigraph is a convex set. Another reason to be interested in epigraph. Now, in this picture, you see a point x bar distinguished, and you see a little green line. This represents an affine function, affine meaning linear plus a constant, an affine function that supports the epigraph of this case. In fact, if you look at the points on or above that green line, that's the epigraph of that function, that would be a closed half space that supports the epigraph at that point that you see in this picture. Anyway, that green thing has a slope vector. This is supposed to be higher dimensional. It has a vector v, which is a slope vector, and the vector v that you get there is something that's called the subgradient of the function at this point. So depending on the circumstances, there could be one of those, there could be more than one, or even none. But anyway, you are ending up with a closed convex set of subgradients at each point, and therefore, in this concept of generalized differentiation, very different from the concept in the theory of distributions, we are associating with this function f a certain set-valued mapping, its subgradient mapping. And by the way, this mapping it's able to determine f uniquely up to an additive constant. You can integrate this mapping to get the function f back again. You can also view this, the subgradients, as coming out of the normal cone to the epigraph. So here's an interesting characterization that there is a unique subgradient if and only if the function is differentiable at this point, and that subgradient is the gradient. Another one is that 0 is a subgradient if and only if you have a minimum there. And furthermore, normal cones are special cases because the subgradient mapping, the normal cone is a subgradient mapping associated with the so-called indicator of the set C. That's the function. Indicator is a function which is 0 on the set C and plus infinity outside the set C. So to study normal cone mappings, we can embed this in studying something more. subgradient mappings. Now here's a difficult problem. We have, well, a difficult issue. We have something which is so important to solve, and we can't think of a good name for it. There aren't too many situations like this in mathematics. So everybody knows the importance of solving equations. There's no discussion needed for that. But we need to go beyond to something that's not quite an equation, but there isn't a good term for it. People have played around with different ideas. In this talk, I'm using the term generalized equation. So a generalized equation is something that could, in a special case, become an equation. So it's not terribly different. So I'm thinking of a set-valued mapping from Rn to itself. And what I want to do is find an x bar such that the set T of x bar contains 0. I didn't used to like this notation, but I've come to find it very convenient. So an example would be, if this is a subgradient mapping, I want to find a point where the minimum occurs. Or if it's this could be a mapping coming from a variational inequality. It could be this, f plus the normal cone mapping. Then, to solve this generalized equation would be to solve a variational inequality. Now, for set-valued mappings, you have slightly different concepts of what the graph is. The graph should be a subject to the product space, not involving a space of sets. The effective domain are the points where the image is a non-empty set, and so forth. So these different ideas are useful here. And the inverse of a mapping always exists. You just have to reverse the pairs in the graph of the mapping. So here's a picture of a set-valued mapping which looks a little special. It is quite special. But on the other hand, it's typical of the applications we wish to make and helps to justify why we feel so strongly about some word, some term like generalized equation, because these things are so near to being equations. I'm showing here a graph of a mapping. This is set-valued, right? Because if I take a point here, I can get several images. You might wish to think of it as a multi-valued mapping. I do avoid that term usually. Now here, the points where 0 is in the image are here. It's a set of solutions. Still, there's something very function-like about this mapping. It's because this mapping has a graph, which is a sort of a Lipschitzian graph. It's a Lipschitzian manifold, and this is a kind of property that is required to be studied and understood. The main area in which this property occurs is that of a so-called monotone operator. Monotone operators were introduced in the area of PDEs, but they also are equally come up in optimization. Here we're looking at a finite dimensional version. Monotonicity in this case is not related to a partial ordering. It's monotonicity as a generalization of positive semi-definiteness, unsymmetricness perhaps. So monotonicity means that if you take two pairs in the graph, x1, v1 and x2, v2, and you look at the inner product of the differences, you'll get something non-negative always. And a mapping is maximal monotone if its graph cannot be enlarged without destroying the monotonicity. So if you have a continuous single-valued mapping, monotonicity already implies maximal monotonicity, but not in general. And for a smooth mapping, it would correspond to positive semi-definiteness of the symmetric part of the Jacobian at every point. But that's the set-valued ones we're so interested in. So examples that have this property are subgradient mappings for convex functions, in particular normal cone mappings, the mappings that correspond to variational inequalities when the f is monotone, and the inverse of any maximal monotone mapping is maximal. And these mappings have so many powerful properties. The image sets are always convex. Their effective domains and ranges are virtually convex. Only some boundary points might be missing. They are single-valued and continuous almost everywhere in the interior of the domain. Many such things. And their graphs are, in fact, homeomorphic in a Lipschitzian manner to Rn. So they correspond to something like the picture we saw. Now I'll explain here why something now about this Lipschitz property. The resolvent of a maximal monotone operator. For a general lambda greater than 0, it's you take I plus lambda times the mapping and take its inverse. That's the resolvent. And that, it turns out, is always a single-valued mapping that's non-expansive. It's Lipschitz continuous with a constant less than or equal 1. It could be contractive if you have what's called strong monotonicity. So here I've drawn a graph of a set-valued mapping. This is set-valued, right? Because at some places I can get more than one image here. There's a whole interval of images, and this is just a two-dimensional picture. But this is a set-valued mapping, but it's so function-like. And it has this property that if you take any of these transversals you see here, given by the equation, this is the x-axis and the v-axis, x plus v equals z, there is a unique such point. And the x is given by this, by one resolvent, and the v by a resolvent of the inverse. And this, in fact, is a Lipschitzian parameterization of this graph. So in the and you can calculate these. So in the subgradient example, you have to calculate this, you solve a minimization problem. In the normal cone example, if that's a normal cone, it's simply finding a projection on the set. So these are, although the resolvents might be abstract things in some areas, here they are not. So now to finish, all I can do is mention some numerical approaches that depend on this. And this is one of the areas in which people at IMPA have been especially active. So you want to solve a generalized equation, and there are many important cases where it's maximal monotone. One kind of approach you can take is called the proximal point algorithm, where you generate iterations through resolvents. The parameter in the resolvent becomes the numerical step size, or what's called the step size. And it can vary from iteration to iteration. You form a sequence, and under very simple assumptions, a sequence will converge to a solution to the problem. Then besides that, there are many refinements. Many people have worked to make this a much stronger subject. There are, of course, infinite dimensional applications to this as well as finite dimensional. Another broader idea is that of a forward-backward splitting, where the operator you have is the sum of two maximal monotone operators. And you can do something which corresponds to taking a forward step on the first operator followed by a backward step on the other operator. The backward step involves this resolvent, and you generate iterations that way. And there are many applications of this to variational inequalities and the like. So I just wish to conclude by, since I didn't give many references in the talk, I just put down a couple of references. A book written by Roger Wetz and myself, Variational Analysis, in the Springer Verlag series on Grundlehre, came out several years ago, and is a large book. It's pretty comprehensive. It explains all these ideas of analysis, the normal cones and subgradients, even beyond convexity, and it's a pretty good way, if you have some interest, to see how all of this is going in this other direction of analysis. And then I've just added a couple of other things having to do with these more applied things like these numerical methods. This is just one paper, but it happens to have a big bibliography that refers to a lot of work and a lot of methods. And finally, a subject I didn't have the time in this lecture to talk about, questions of the effects of perturbations of solution in all the analysis. There's a forthcoming paper that would serve that purpose. That's all. Thank you.
Is there any question? No? Let's thank Professor Rockafeller.